Welcome to the channel Physics Made Easy. Today we will discuss rolling motion on an inclined plane. On an inclined plane, if the object is rolling and there is no friction, the plane is perfectly smooth, then it will skid, it will slip. How the role of friction, what is its required value, what is velocity, acceleration, we will discuss in this video. Today we are going to discuss another phenomenon of rolling motion, that is on an inclined plane. We already have discussed the rolling motion on a horizontal plane. What is rolling motion? Combination of translational motion and rotational motion. As we have discussed in previous videos, that for an object which is having its center of mass, that is whole object, translational motion is represented by Vc and the angular speed omega for all the particles. Then lowermost point P of the object at the horizontal surface, suppose this is the horizontal surface, then it will also have the translational motion in this direction Vc and the tangential speed, that is r omega if the r is the radius of the object in the opposite direction. This rolling motion has the combination of translational plus rotational motion. This is translational speed, this is rotational speed. What about pure rolling? We all have discussed this earlier. Pure rolling means the lowermost point must remain at rest. That means if this is the ground, then with respect to ground, it should be at rest. What is the speed of ground if you say 0? Then what is the speed of lowermost point P? This is forward, this is backward. So this is Vc minus r omega. So for pure rolling, there should be no relative motion between the lowermost point and the ground, or you can say that this difference should be 0. So Vc minus r omega is 0. Hence Vc equal to r omega. We all have discussed it earlier and it is true for the fixed ground. The surface at which the object is rolling is stationary. Also we have proved that if the surface at which the ball or the point is rolling, then this surface is a platform which is moving with the velocity v0, then what will be the condition? This Vg ground will have the velocity v0. Then for pure rolling, we will get here Vc minus r omega equal to v0. Therefore omega will be Vc minus v0 upon r, and this is the ultimate condition for pure rolling. Here if platform is not moving, ground is stationary, then Vc by r. Most of the cases we see that the object is rolling at the stationary ground. Similarly for the accelerated motion, we also have seen for accelerated motion, let the center of mass of the body which is rolling have the acceleration acm, and acceleration produces angular acceleration also. So this lowermost point has this acceleration in this direction ac, and due to the rotation, which acceleration? Angular acceleration in this direction. So angular acceleration, due to angular acceleration, a tangential acceleration at equal to r alpha is produced backward. Again we can derive the expression that for pure rolling there should be no relative acceleration in the of the lowermost point P with respect to ground. So what will you write here? This AC minus R alpha is 0. Therefore AC equal to R alpha is the condition for the pure rolling. These two expressions we have derived. Also again, if you put the platform P which is moving with the acceleration a naught at which this object is rolling. Then for moving platform, for accelerated here, for accelerated platform, what will you write here? This condition will become, this alpha will become AC minus A naught upon R. Okay, so these expressions we have discussed earlier. What will happen today? That we are going to discuss the rolling on an inclined plane. If this is the inclined plane having angle of inclination theta, which can give sufficient friction, which we will see later on. So if this is the inclined plane having height h, this distance s, angle of inclination theta. Any symmetrical object, ring, disc, hollow or solid cylinder or a sphere, it is here at the topmost point. Okay. What happens if I draw here at the topmost point? This is the ring or any symmetrical object at the topmost point. We can see that the weight of the object vertically downwards. So if this is the inclined plane, then weight will act vertically downward. Okay, this is mg, this angle is theta. So you will find that mg has two components, this and perpendicular one, this. If this angle is theta, this will be theta, though this will be mg cos theta, and this is mg sin theta. Normal reaction perpendicular to the plane, this will be n. What will happen if the inclined plane is smooth? We are going to discuss on the for the rolling on the inclined plane. Let us think imaginary plane which is perfectly smooth. Since there is no motion perpendicular to the plane, so we will take only the two components like this. If I show here that this is the plane here, then this is the mg sin theta and this is n. Okay, the smooth plane is there, angle of inclination is theta. Look, this point is center of mass. Both n and mg sin theta, they are passing through the center of mass. Will they constitute any torque? No, because force passing through the center of mass will not constitute any torque. R cross F, theta will be 0. There is no torque. Then will the body roll down? Will the rolling take place? Because rolling requires torque. These cannot form torque. Then what will happen? The body will slip, skid. There will be no rolling because there is no friction, no torque, as the plane is smooth. So note down that for the rolling to take place on the inclined plane, friction is necessary. Now we will take a plane at which friction occurs, that is the plane is rough. Now what will happen if the rough plane is there, if its height is h and angle of inclination is theta, which can provide sufficient friction. The angle of inclination is suppose that is this one, this is theta to provide sufficient friction, and if this is the height h. Okay, now if you see that the normal reaction and this mg sin theta, out of which only acceleration in the downward direction is a equal to g sin theta, and if the friction is smooth, then only this acceleration will provide only the translational motion, not the rotational motion. As I discussed that for rotational motion a torque is necessary. There is no torque formed by these forces, so no rotational motion, no rolling motion, only the translational motion or skipping or sliding of the body will take place for the smooth plane. If the plane is rough, what will happen? The friction will act in this direction, in the tangential direction, opposite to the motion. Will it or not? Friction opposes the motion. So look here, it has tendency to come down and the friction is acting upward. Then what will be the net translational motion? How will you write the expression for that? If the object of mass m is coming down with the force F, then what will be this net force? Net force will be equal to mg sin theta, that is the net force downward, minus frictional force which is acting on the upward direction. This F net can be written as mass of the object into acceleration. So this is the expression number 1, and this expression is for translatory motion. Okay. Now rolling consists of rotational motion also, and since the plane is rough, then rotation will take place. This friction is acting in this direction and it will rotate the object in this way. Will it or not? Look here, this is the object of symmetrical object of radius r and mass m. Then this friction will rotate the object and produce the torque. This tangential force will produce the torque, anti-clockwise torque. You know, torque is given by this I alpha, and due to rotation the angular acceleration alpha will be produced. And what is the torque formula? This is R cross F, or here this R and F both are, this is R and F, both are perpendicular to each other. So you can find here that what is this frictional force. I am representing with the small f. Then how will you find what is F? This F can be written as I alpha upon R. This is expression number 2. This is for rolling. Here this F equal to I alpha upon R, if you put in this expression, you will get mg sin theta equal to ma plus I alpha upon R. Now for the rough surface, we have seen friction acting along the surface upward and net acceleration with which the body is falling downward, that is A, and this is the equation for translatory motion. Here at the lowermost point, if you see that at the lowermost point, for this point P, we see that the friction produces angular acceleration in the upward direction, and lowermost direction the acceleration is A. So the relative acceleration of the lowermost point with respect to inclined plane is again 0. That is the condition for pure rolling. At the leveled surface we have discussed, it was AC equal to R alpha. AC was the center of acceleration of center of mass. What is here? This acceleration in the along the plane in the lower downward direction, and friction produces angular acceleration. This is along the tangential direction at the lowermost point P in the upward direction. So what happens that we can write here these two expressions for relative acceleration at the lowermost point to take place 0. We can write here this A, and this tangential acceleration is, this is R alpha, this is R radius of the object. So A equal to R alpha, again can you write that alpha is A by R here. Then in place of alpha you put here the pure rolling condition at the inclined plane also, alpha equal to A by R. So you take M, you can write here this is MA plus IA by R square. So if you take A common, then what will you get here? This M plus I upon R square. Therefore, what is these all are capital M. Okay. So what is the acceleration in rolling motion on the inclined plane? If you write here, then acceleration is this mg sine theta upon m plus I upon R square. And look here that acceleration is not g sine theta as we have discussed for the smooth plane. Here friction is existing and acceleration in the downward direction is less than g sine theta. If you put the value of I for the rolling object, for the cylinder, for the disc, different values of I along the axis of rotation, put the value, you will find the acceleration on the inclined plane. Now in this expression for acceleration, if you divide by m, you will get this acceleration g sine theta upon 1 plus I upon mr square. So this is the expression for acceleration. Since this acceleration is constant at the plane, for constant acceleration we can use the expression v equal to u plus at. You know this expression for constant accelerated motion, the equation of motion. We have seen here that in the beginning the u initial velocity is 0, then to find the value of velocity for the inclined motion, motion of the rolling object on the inclined plane, we will write this v equal to at. Then what will be here? A, you put the value, you will find what is the value of velocity. How will you find that? You know v equal to u plus at requires time, t expression. So you consider the third equation, v square equal to u square plus 2as, because we can have this value s and this is h. Then what can you write? This h upon s is sine theta, then s will be this h upon sine theta. So we can use the third one expression. What will you get here? This is 2 into a, put the value of a, g sine theta upon 1 plus I upon mr square, this total, into s. S means this h upon sine theta. So sine theta will be cancelled. What will become v? This under root of total expression 2gh, this is 2gh upon this 1 plus I upon mr square. What we observe here that expression of A involves the angle of inclination and expression of V doesn't. Learn this expression also for the velocity on the inclined plane. Again, we have seen that for the motion on an inclined plane, due to the friction, the r omega is the velocity in the upward direction, and in the lower direction, downward direction, velocity is v. And at the point of contact for the pure rolling, what we have got? This expression that at the point of lowermost point must remain at rest. So this lowermost point, this r omega minus v should be 0, that is v equal to r omega. That condition of pure rolling is fulfilled. So we have discussed that for pure rolling, what is the condition for velocity, expression for velocity and acceleration. We have noticed one interesting point, that pure rolling, there is no relative motion, even friction is present at the surface. Because of the friction, this rolling is taking place. Smooth surface, there was no friction, there was no rolling, only the skidding or slipping of the object. The object was slipping or skidding on through the inclined plane. Only the translational motion was there. So for rolling, the role of friction we have seen at the inclined plane. Which type of friction is this? We have seen a static friction, kinetic friction, then which type of friction? Look, at every point, since there is no relative velocity, the lowermost point is supposed to be at rest for the pure rolling. Then at rest, which friction? Static. So this friction is static. What you do the mistake, that you have learned that friction is also written by this F equal to mu n, and you write this mu mg cos theta, because n we have taken here, this was mg cos theta. This is the maximum value of the friction, or you can write this F maximum is F limiting, maximum value of the limiting friction. So it is not applicable here. Here, whatever is the inclination, as per inclination, whatever may be the requirement of static friction. Static friction is the self-adjusting. What will be that value? What static friction will be there? Let us find. We have got these expressions, and for translational motion and rotational motion, we have got this expression that mg sin theta. Earlier we have written this expression that mg sin theta in the downward direction minus F was the resultant force ma. And from this expression, if you find what is F, you can find F as mg sin theta minus ma. This mg sin theta minus ma, if you put the value of a, then what will be this? Mg sin theta minus m into g sin theta upon 1 plus I upon mr square. Take mg sin theta common, you will get here this 1 minus 1 upon 1 plus I upon mr square. What will you get here? This mg sin theta, this mr square will go up, and mr square plus I, and here this mr square plus I, you will get here, this is mr square plus I minus mr square upon I plus mr square. So this mr square will be cancelled. So the static friction or the friction required as per the value of inclination is only this mg sin theta I upon I plus mr square. Learn this value also, and as per the object value of I you will get the required friction for solid cylinder, hollow cylinder, sphere, whatever may be the object. Now we have calculated A, V and F for the friction, and never assume that this friction acting here is the maximum value of friction, that is limiting friction. It is a static friction whose value is this. Then what will be the coefficient of friction at the surface? How will you find? Look, I am going to calculate here that sometimes it is asked that find the coefficient of friction of the plane. Then we know for rolling, what is the condition of rolling? That condition of rolling, that required pure rolling, required friction should be less than F maximum or limiting friction. Required friction is this much and maximum friction is mu n g cos theta. So if you write this mg sin theta, this is I upon I plus mr square, and this should be m mu mg cos theta. Then what will be mu? Look here, this will be mg and mg cancelled. This is tan theta and I upon I plus mr square. So these are the expressions which you have to learn, that for solid cylinder I is mr square by 2. If you will put, then you will get the value of frictional force. You put I mr square by 2, then this will be 3 by 2, this will be mr square 2 by 3, will be cancelled, then you will get this frictional force. You can also have acceleration and velocity as per the symmetrical object's moment of inertia value. So to prevent slipping, to have perfect rolling, what should be the coefficient of friction of the plane? This we have discussed. And what is static friction of the plane, acceleration and this velocity of the rolling object. I hope you must have enjoyed. Look, this question, a disc rotating about its axis with angular speed omega naught is placed lightly without any translational push on a smooth table, perfectly frictionless. This is the table. As shown in the figure, you have to answer these questions. First part, what are linear velocities of points A, B and C? These points are on the disc. Look, A is the topmost point, B is the lowermost point and C here at the distance of r by 2 from the center. You know, omega naught is the speed of angular speed of rotation. We know that V is given by r omega. Then for the point A, at the topmost point, VA will be r omega in the direction of the arrow indicated. And what will be VC? That will be r by 2 omega. This will be also in the direction of the arrow. What will be B? Speed at B. VB will be r omega again, but you know, rotation takes place like this. So in the direction opposite to the arrow indicated. These are the speeds. Will the disc roll in the direction indicated? Since the table is smooth, frictionless, so the disc will not roll. Why? Because rotational motion requires this torque. So there is smooth table, there is no friction, no any tangential force, so it will not roll. C point, explain why friction is necessary to make the disc roll in the direction indicated. As I told, to roll a disc, torque is necessary. In turn, to produce torque, a tangential force here, force of friction, it will be there if then the torque will be produced by it. Look, this is the radius, this one is, and then force of friction if present at the table, only then the rolling will take place. So why friction is necessary? It is asked that friction will make the disc roll to produce the torque so that rolling occur. For rolling to take place, torque is necessary and torque will be produced by the tangential force. This force is the force of friction, that's why. D part, give the direction of frictional force at B and direction of torque before perfect rolling begins. You know, friction's role is to oppose the relative motion. What is the motion at B in this direction? Due to rotation, V equal to R omega in this direction. So what will be the direction of action of the frictional force? Opposite to that. So friction will be here indicated in this direction of arrow here. It will be. So direction of the frictional force at B will be in this direction, and torque. What will be the torque? Look here, this frictional force and R cross F. F is 90 degree, torque is R cross F. And what will be the sense of direction? Look here, this R cross F, that will be anti-clockwise. This is R cross F. So out of the paper or anti-clockwise. Look here, this R cross F, right hand thumb rule. Okay, direction of torque out of the paper anti-clockwise. How it is determined? By the right hand thumb rule. Friction will act in this direction. What is the force of friction after perfect rolling begins? You know, role of friction is to decrease VB. If you denote here, this will be the direction of VB. Then what is the role of friction? To decrease this speed. What happens that rolling begins when this VB becomes 0. Once it happens, frictional force becomes 0. So there will be no force of friction after perfect rolling begins.